Hello everybody, welcome to Huawei eLearning service. My name is Matthias Ellerbeck and today we have the course LTE System Overview. The course is divided in 3 chapters. So first of all we will see a global network architecture, then we will go into the air interface principles of LTE. This means we will see how the air interface in LTE is designed. And last but not least, we have a small chapter which is called eNodeB Product Overview, where we will see what products are offered by Huawei for eNodeBs, and eNodeBs are the stations in LTE. So we will start with the network architecture. This chapter again is divided into 3 subchapters. First of all, we will talk about the evolution of cellular networks. How did cellular networks evolve over time since the 1970s? Then we will go to the EPS architecture. EPS depicts the PS core and also the RAN system of LTE. We will talk about this. And the third subchapter of chapter 1 is the protocol stack that is used in the so-called EUTRAN radio system between the stations of LTE, but also between the stations and the core network. So let's start with the evolution of cellular networks. First of all, they were launched commercially for the first time in the 1970s and 80s. In 1976, the so-called AMPS was launched in the US and parts of Asia. And in Europe, the so-called system TACS was launched. Both systems were analog systems using frequency modulation, but both systems were not complementary. This means there was no interworking possible between the 2 systems. Also, there was an enhanced version of TACS, which was launched a few years later, and the interworking to the other systems was also not possible. So the big step from the first generation mobile networks to the second generation was the digitalization of the networks. This means that in the second generation mobile radio networks, the information was transmitted in digital, so in bits, in ones and zeros. Therefore, the spectral efficiency of the second generation mobile networks was much higher than the first generation mobile networks. The most common second generation mobile network is the so-called Global System for Mobile Communication, GSM, which is using a so-called frequency division multiple access. We will see what division multiplex means, and we will also see what frequency division means. But there were also other systems like CDMA1, which were using a slightly different way of dividing one user from the other. It was not so common, but both of them were further enhanced to the so-called third generation mobile networks. So usually after GSM, there comes UMTS. The third generation mobile networks had as a largest advantage, they had a higher data throughput. Customers were asking more and more for data services, and this means that, for example, UMTS was designed to have more data throughput. There were also other third generation mobile radio systems like TD-SCDMA and an enhanced CDMA version, which was called CDMA 2000. In the third generation, also WiMAX was designed the first time and further enhanced to the fourth generation. In the fourth generation, we see here that LTE Advanced is written down. Why not LTE? Because LTE is not fulfilling all the presets of the fourth generation. This means LTE is often called a fourth generation radio network, but it is not in reality. We will see why this comes. So we are now talking about LTE, which is more or less between the third and the fourth generation of mobile networks. There was also a further enhanced CDMA version, which was called UMB, Ultra Mobile Broadband, but as well as WiMAX 802.16m. Both of those systems are not very common. So the most common one is LTE and LTE Advanced. Also, LTE evolves and evolved over time. So in the beginning, LTE was only made up by so-called macro cells. This means quite large cells interworking with each other. Then there were also raised so-called LTE A, B, and C. A is already raised. So for example, in the Huawei system, here was a 500% higher cell edge throughput possible. And in general, the network is going more and more to a heterogeneous network. This means that per macrocell, we have more and more small cells, femtocells, picocells, things like this. With LTE-B and LTE-C, we will have a further and further increased number of small cells per macrocell. Also with LTE-A, which is part of LTE Advanced, we have new features like carrier aggregation, coordinated multipoint, and so on. Therefore, we have higher and higher increasing data rates, and we are going to a further and further advanced network. So, what does LTE mean? There were some requirements that were asked for by the ITU, what LTE should be able to do. And then the 3GPP, the third generation partner project, designed LTE in a way to support these requirements. For example, the bandwidth should be flexible. This means that operators, also operators who have only small bandwidths available, could support LTE. Therefore, the 3GPP designed 6 different bandwidths for LTE from 1.4 MHz until 20 MHz. Another thing was that the spectrum efficiency should be higher than in the third generation, and we see that LTE ended up with 2 to 4 times higher throughput, higher spectral efficiency than the third generation mobile networks. The peak throughput for the large cells, here for the 20 MHz cells, should be at least 100 megabit. LTE is now able to support up to 300 megabit. With LTE Advanced, we also go into 600 megabits, even beyond 1 gigabit per second. And only then, when we have more than 1 gigabit per second, we can really call it a fourth generation mobile network. We wanted to have small latencies for control plane and user plane, which was designed to be fulfilled by LTE. We also should make sure that when people are traveling with high speed, for example in trains, they should still have a significant data rate. For example, in LTE, we have at least 100 kilobit per second at high speeds, and so on. Another thing that it was completely skipped in LTE is the CS domain. This means LTE is only packet switched, and we have no circuit switched services available anymore. This means we also have voice over IP to support. And the hierarchy should be more flat. This means less controllers. This again means that the stations, the eNode Bs, have to talk directly to each other. And because this makes a network quite complicated, there should be the so-called self-organizing network features, zone features, introduced. So this was the first subchapter of chapter 1. Now we will see how this architecture and the flat hierarchy architecture was designed in LTE. What we directly see when we know 2G and 3G networks is that there is no controller anymore. This means after the station, we have the direct connection to the core network. No base station controller, no radio network controller. The stations are connected to a so-called MME, mobile management entity, and to a so-called serving gateway. Here, the control plane is completely diverted from the user plane. For signaling, the station is only communicating with the MME. For user plane, it's directly communicating with the serving gateway. There is no user plane data, no packets going to the MME or through the MME. So, what we have further down in the core is also, of course, a database, home subscriber server, and a so-called policy and charging rules function, which maintains the so-called quality of service. We will see what this means later in this course. Here we also have to talk about the wording and the abbreviations that are used in LTE and EPS. So LTE, long-term evolution, depicts the radio network, which is also called eUtron, evolved UTRON. UTRON was the radio network of the third generation. SAE means system architecture evolution. and is used to describe the packet core, which is also called EPC, Evolved Packet Core. The whole system in total is called EPS, Evolved Packet System. So when we talk about LTE, usually we only talk about the radio side. So the interoperability between LTE and the 2G, 3G networks has, of course, also to be maintained. Here we see the stations of the three different generations, second, third, and fourth generations, from GRAN, UTRAN, and EUTRAN. Here they are already shown together with their controllers. This means that in LTE or EUTRAN, we don't have a controller. They are interconnected through interfaces. We already know the GB interface in 2G, the IU interfaces in 3G, and the EUTRAN stations now are connected through the S1 interface to MME and serving gateway. We know that there is an S1 control plane interface to the MME and an S1 user plane interface to the serving gateway. The LTE and SAE components are connected to the 2G and 3G nodes of the core network, for example, the SGSN, but also interconnected to the databases. So all the interfaces which are newly introduced with LTE to 2G, to 3G, but also within the LTE system have an S and a number. For example, here the S11 interface and the S4 interface, but also the S3 interface. There are also so-called untrusted non-3GPP networks, which have also to be supported. But for this, we have to introduce a new core network element, the Packet Data Gateway, which maintains the security of our networks so that the interoperability is there, but we are also still secure. So when we go from left to right through the components of LTE, we will start with the UE, user equipment. This can be a cell phone, this can be a tablet, this can also be a netbook or notebook. And this UE has a certain number of identifiers. We all know them from other systems, or we know parts of them from other systems. For example, the IMSI, International Mobile Subscriber Identity, which is encoded on the SIM card. The IMEI, we also already know, is the so-called International Mobile Equipment Identity and is encoded in the equipment itself, so in the cell phone, for example. Now, we have also the globally unique temporary identity, which is also depicting the last MME we were connected to. So this is already LTE specific. And to not always send our IMSI over the air, we also have so-called temporary mobile subscriber identities, TMSIs, and they are slightly different between the second, third, and fourth generation of mobile networks. Here we have the so-called S-TMSI. One identifier that is always there when we are talking about packet-switched traffic is the IP address. And as we already said, in LTE, we are only talking about packet-switched traffic. This means every UE always will have at least one IP address. This can be either version 4 or version 6. The UEs itself were categorized in 5 different categories when LTE was launched in release 8 by the 3GPP. And these 5 categories differ in the modulation schemes they support, in the MIMO they support, and so on. And this all results in different downlink and uplink speeds. What is also mentioned here is that the 5th category already supports 300 Mbit per second in downlink. And this is only possible because it supports 64 QAM as a modulation. We will see what this means in a few slides. So the next component from left to right in the overview picture is the station, the so-called eNode B. We know that the station in 3G was called Node B, and now we have an evolved Node B, which is, as we already said, not connected to a controller anymore. This means eNode Bs are interconnected through the so-called X2 interface. The eNode B is there to maintain all the resources on the air interface. So for example, the radio resource management, the radio bearer control, and the mobility management. All three things are done together with the MME, the mobility management entity, because the MME is always overruling here in this case. The eNode B has two very important identities. One is the tracking area identity. So every eNode B or every cell of an eNode B is part of one tracking area. This means that we do not have to tell the core network whenever we are walking around or driving around one tracking area. And this means we have to do less location updates. And the other one, of course, is the so-called EUTRAN cell global identifier. So every cell of an eNode B has to be a unique identifier that is not there in the world a second time. How is this maintained? This is very easy. The evolved or EUTRAN cell global identifier is made up from mobile country code, mobile network code, eNode B ID, and then in the end, the cell ID. One of the most important things an eNode B has to do is to schedule the requests or the data packets that are transmitted or received from a user equipment. We will see how the scheduler works later in this course. Now, as we are talking about LTE here and not so much about SAE, we only have one summary slide for the three core network elements we already talked about. One is the MME, which is a complete which is only there for signaling. So it is without any user plane packets, a core network element without any user plane. And it is there for mobility management and session management. Mobility management means, for example, handovers when the user changes the cell. Session management means bearer management. So when a user has a data stream, it gets a bearer. When a user equipment has another voice stream, it gets another bearer. This is session management. The MME is also doing authentication and key management. This means it talks with the eNode B and the UE on the one side and with the databases further down in the core to make sure that only registered and authenticated users can access our network. Behind the MME is the serving gateway, which is there for user plane. This means packet forwarding and routing. This forwards packet either to the user equipment or from the user equipment. This can also do IP header compression, and whenever there is downlink packets arriving, but the user has to be paged first because the network does not completely know where it is at the moment, the packets have to be buffered. This is also the point where legal interception or lawful interception can be done. Last but not least, the PDN gateway, Packet Data Network Gateway, is also, of course, forwarding and routing packets. And it is the IP anchor or the 3GPP anchor of our user equipment. This means our user equipment will always be connected to one packet gateway, which then forwards the packets to non-3GPP IP networks, for example. The packet data network also allocates the IP address to our user equipment, one or two IP addresses. So this was the second subchapter of chapter 1. Now we come to the third one, which is the protocol stack structure. We already said that we have more or less three interfaces we have to talk about. The first one is the interface between user equipment and station, the so-called UU interface. Here we have to divide between control plane and user plane. The control plane, so the signaling, is done either directly to the eNode B via the RRC protocol, radio resource control. Here we set up signaling radio bearers, but also radio bearers for user plane traffic, and the non-access stratum signaling, the NAS signaling, to the MME. This signaling is also going through the eNode B, but is directly forwarded from the eNode B without the eNode B looking into those packets. The protocols which are further down are radio protocols, PDCP, radio link control, and MAC layer. So they are there for example, header compression, segmentation of packets, concatenation of packets, and on the physical layer, they are then transmitted. The user plane protocol stack looks very similar, but of course we are lacking the signaling protocols. So here we are only talking about PDCP, radio link control, MAC layer, and the physical layer. The next interface we have to look at is the so-called S1 interface. Here again, we have to divide between control plane and user plane. The S1 control plane is between eNode B and MME, and it is made up from down to up by the physical layer and the data link layer, of course. Then we have IP and SCTP for security, and on top we transport the S1 application protocol. The user plane does not support the SCTP, but here we transport the packets via UDP and GTP. On the X2 interface, this looks very similar, because here we only have the interface between eNode B and eNode B, so we have to forward more or less the same signaling and user plane packets. So here we also, in the control plane, are talking about physical layer, data link layer, then IP, and then SCTP. The overlying protocol is called X2 application protocol, because here we are talking about the X2 interface. The user plane is also IP, UDP, and GTP transport. In the end, we have a small summary. So what did we learn in this first chapter? You should remember that LTE was initially released by the 3GPP in their so-called release 8. That our EPC, so the Evolved Packet Core, is made up by 3 different network elements, the MME, the Serving Gateway, and the Packet Data Network Gateway. That there are no CS services supported anymore. All traffic is going over packet-switched services. And that our eNode B, so the central network element when we are talking about LTE, is connected to the MME through S1 interface, S1 control plane in this case, and to neighboring eNode Bs through the X2 interface. So far for chapter 1. Thank you for watching.